Okay, so this is what we're going to talk about. And sorry, apparently I'm having more trouble with these slides here than I expected. So I'll read it off the screen. So first I'll just talk a little bit about what a macro is, or some ways to think about it. We'll define what we mean by illuminated macros. Talk a little bit about how Racket illuminates macros, and then Jonathan will talk about how we can do illuminated macro things in Clojure. So, a macro is a compiler hook, right? When the Clojure compiler is going through its normal process, when it sees a reference to a macro, it'll call out and let you do arbitrary code, right? So whatever you want to do, you have a hook into the compiler through a macro. But actually, the code you do there, whatever that arbitrary work is, returns more code, right? So, a macro is a compiler. It takes code from one language and produces it in another. Now, colloquially, we talk about both the input and the output forms being Clojure, but they're not really the same language. So here's an example of that. This is a macro that you might write if Clojure didn't have its own let, right? This is kind of the scheme definition using an anonymous function and then calling it to simulate let. So the input to this macro is a language that does have a let2 form, right? It understands what let2 means. And the output of the macro is code in a language that doesn't have let at all, but only has anonymous functions. So this is a compiler from one language to a slightly more basic language. So a macro is a compiler. But a macro is also a function. And in Clojure, they're even implemented as functions. It's just a regular function that's tagged so the compiler knows how to call it slightly differently. And like all functions, macros are best when they're referentially transparent, right? When they're pure functions. You can, of course, as you can in a Clojure function, do any crazy thing you want, but most of the time it's best if they're pure functions, that they just take their input and return their output and don't have any side effects besides that. Many functions, so this is that same macro I just showed. Many functions do three kinds of things. One of the kinds of things is collect input. We often use destructuring for that, and then sometimes need to do some more work besides. There's often a part that computes. You can see here the computation part is sort of, well, that's not right at all. Okay, yeah, well, so you can see the destructuring, that's where we're collecting input. The take nth forms there are computation. So here it's sort of intermingled, the computation and the output. But then that syntax quote form is the output, right? And so those are the three kinds of things that a lot of functions do. Not always separated. Some functions leave those one or more of those out. They don't need to, for example, do any computation. And in fact, we see that in macros, which are functions, we might use slightly different terminology. We might say actually emit and maybe even parse up at the front because it's a compiler, right? It's analyzing its input. It might be doing a little bit of parsing. So I mentioned these three kinds of things because we'll come back to that as we go along. Specifically, I think that often when we're writing macros, we either don't need to or don't think we need to do any computation. Once we've understood the input, we can just go straight to the output. I'm sure that people who have looked at the core async Go macro are aware that sometimes you do need to do some computation in your macro. So, all right, but what do I mean by an illuminated macro? So Jonathan and I have been sort of pondering some of these things, and specifically the sorts of things we'd like to see in a macro. And here are some of the things we came up with. This isn't, it's not a perfect list or anything, but it's some of the things that we think would be nice that we only see various degrees of success in macros that currently exist. So syntax documentation. By that we mean that when you look at a macro, it would be great to be able to understand how to use it. Just look at the documentation and understand what forms and what order, what they mean. So good documentation. In whatever form, whether it's textual, maybe a BNF notation would be nice to understand what input a macro needs, or maybe a railroad diagram. I don't know, I had a Turbo Pascal book that I loved because it had railroad diagrams for all the syntax. There's also syntax error messages. So for a given input that's incorrect, it would be great if we saw a report that gave you the nature of the problem, where the problem occurred, and maybe even an example of what would have been valid input or a description of what would have been valid input instead. visualization of parsing for a particular input. So this is something that I don't think we've actually seen anywhere, but it would be interesting if when you gave a specific form to a macro, if it could tell you how it interpreted, what parts were understood as what. So think about, destructuring or the optional parameters to the defin macro. If you could give it an input and it could tell you how it understood each of those parts to be. And then visualization for the output. Now we have macro expand, right? And that's something, but it'd be pretty neat if, for example, you could tell from the output of macro expand which parts of the macro form came from the macro itself and which parts came from your input. It might help clarify what's going on there. And of course, the important thing is that it should be easy to do all these things. We can do all these to some extent or other now, but it's all handwritten and re-implemented by each macro writer. So it'd be nice if there were tools to help us do this better. But it's certainly not easy now. So here's, I'm going to pick on Clojure for a moment. You're not really meant to be able to see all that. That is Clojure's own defin macro definition. It's only an excerpt of it. It's the part that is analyzing the input, understanding the different optional parameters to the defin macro. It doesn't have anything to do with destructuring. This is in a form of the defin macro that's earlier in Clojure core that doesn't do destructuring yet. And there's a couple other things. There's a custom error message that's written up there at the top. You can't really see it, but it's checking for a particular kind of problem and asserting an English error that's meant to be easy to understand. So what happens if you don't do that kind of manual check? Well, here's a quote from a paper that I'll refer to a couple times in this talk. The paper is called Fortifying Macros. And this quote is saying that when a macro doesn't check its input sufficiently, it allows that the macro eventually trips over constraint checks at a low level in the language tower. Low level checking, in turn, yields incoherent error messages. And this was kind of a theme of the paper and the thing that they were sort of harping on, and we'll come to see how they address that problem. But here's an example of what they're talking about. So here's that same let macro. I don't trust the screen now, I have to keep looking. So you can see a couple examples of errors here. So the middle of the screen there, you can see what happens when I give it an extra binding form without a value, right? It says wrong number of args, 1, I don't know what that means, passed to something I've never heard of, right? As a user of the macro, without understanding how the macro is implemented, I have no chance of understanding what that error message means. And in the bottom case there, if you can see it, it's even a little scarier because here I gave it some crazy input and it didn't give me any error at all, it just gave me crazy output, right? So, all right. So that macro was easy to write. Oh, I wanted to say, so sort of a summary of what Clojure gives us sort of out of the box. What we have now is good in a few ways. Specifically, we have this syntax quote, DSL, really, it's a DSL, that gives us a little bit of hygiene, right? But even more importantly, it has an escape, right? It's got an escape tilde that lets you get back out into the regular language. Now, this is something to be wary of in general. If a DSL does not have an escape, it may be that you are trapped, right? So, all right, so let's look at a different approach for writing macros. All right, this is an example of what's called macro by example. This snippet was taken from the Fortifying Macros paper. And it is implemented in Racket. It's a flavor of the scheme language. So I'm going to, checking my time, I'm going to very quickly go through this to say that, so the define syntax, just a little bit on each line. The define syntax is sort of the generic way in Racket to define a new macro. So then the syntax rules is the specific DSL that they're demonstrating here for writing macros. And the key thing to note here is the third line is a pattern that shows what the actual syntax you're trying to match is, right? So it's this let form. And then the last line is the output from the macro. All right, so you've got those ellipses there, which are sort of magical. And you can see that it's doing some kind of rearranging of the terms and somehow it understands the ellipses in different places. And there's very specific rules for how that works. But the result is that it's a little bit self-documenting, right? You can read that pattern and it looks pretty close to what you would have to type as a user trying to use the macro. So it's a little bit self-documenting in that way. So it's one step closer to illuminated macros. But you are trapped because there's no way in here to put between the pattern and the output, there's no way to do arbitrary computation. In fact, there's no way to do computation at all. Somebody noticed this, and well, so I just wanted to mention that you're trapped here. So now it may be, you might accuse me of hypocrisy for wanting to write macros without being trapped by a DSL, when by writing a macro, I'm probably creating a DSL, right? So I recommend avoiding hypocrisy either by not trapping your user at all, or at least providing an escape out so that they can provide regular Clojure code with the full power of the language. Okay, so here is another form of macro by example called syntax-case. It added a little bit more, one more feature which I wanted to point out because it's another of our 3 parts of a function. This guard expression here in the middle is more or less arbitrary code. You can see there it's got special syntax for referring to these magical ellipses variables. But this guard does not participate in the output at all, except to the extent that it causes a failure. So the one improvement we've made here, the pattern is the same, right? So the documentation part is the same. But the guard expression, all it really does is it helps contain the errors to the macro itself. So you don't have things bubbling up from the lower level of the stack like we talked about. So it's a slight improvement. Well, so the authors of the paper, the Fortifying Macros paper, saw all of the weaknesses in this and addressed them all head on. And so here is an example of their solution. So you can see the format there is very similar. Now it says syntax-parse instead of the other ones we looked at. And so they addressed their problems head on by adding things to their DSL. One of the things they added is more syntax patterns. So we didn't really look at it in detail, but syntax-case had really 3 kinds. It had literal lists that were just regular parentheses, unconstrained vars, so there's those vars that were getting matched and used again later, and sequences represented by the ellipses. Syntax-parse has a few more pattern constructs, well, a lot more, really. So they really, handled that problem. They also added some other things to their DSL. They added types to constrain what pattern variables can match. And then they added defined syntax class form so that you can create your own pattern types. They added side conditions, which are like guards, but are more localized and trigger sort of backtracking through the parsing rather than failing the entire case. And then they added the ability to write custom error messages for your side conditions when they fail. Here's an example of let that uses a few of those features, not all of them. So you can see that the one real nice thing that we had from macro by example, which was that the pattern looked like the code it was matching, has sort of been lost. I mean, we've got sort of some of the pattern down here and some of it up there, and then there's a lot of other stuff going on. So it has sort of taken a step backward in the documentation front. But where this really shines is in error messages, because with all these names and descriptions of the patterns, and the way that it's a real parser that's going through and parsing the code that you give it, it's able to find multiple possible errors that it can describe fairly clearly and then choose from among them the one that they think is most likely to be useful to the programmer. So the error messages are really where it really shines. But along the way, they've got a DSL that still has you largely trapped and is indeed somewhat complex and has walked backwards in the documentation. So Jonathan has some other thoughts on ways we could solve this.
Thank you, Chouser. Okay, so this is Ruby. This is Racket. But let's talk about Clojure. We have macros, just like Racket has macros. Those macros, they have syntax, and of course, we would like good documentation for that syntax. So before I talk about the tool that I'm going to present, I wanted to show real quickly what we are dealing with today and kind of the state of the documentation and error messages with Clojure macros today. I'm going to focus on let throughout this part, just as a way of being consistent with the paper that we were reading, referring to previously. Okay, so I highlighted the syntax parts of the let doc string. They're all in green. So you can see that it's, first of all, I want to mention that it's handwritten. Second of all, it's not complete. We have let, which is going to have 0 more bindings inside of square brackets. And then the binding form is missing from this syntax documentation. In fact, that's unfortunate because it's kind of the most interesting part. It's, you can, of course, go to the URL that I've also highlighted in green, but that's hardly, that's basically punting and saying, I'm not going to give you all the documentation, which is unfortunate because the code is written in Clojure and it knows somewhere in this Clojure base what that syntax is. Okay, so let's look at error messages. I have a basic common newbie error message up here. You're going to accidentally try to bind to a keyword instead of a symbol. The exception error, or the error is actually not that bad. You are trying to use a keyword and it's an unsupported binding form. But there is an issue here. If you look at the error message, it's coming from nowhere in the code that you typed. It's coming from someplace else, specifically line 4029 of core. So you're kind of lost if you're new to Clojure. This doesn't help you tell you, it tells you what went wrong, but it doesn't tell you where it went wrong. And for that matter, it doesn't actually tell you what you could have done right. Another example of destructuring, another error message that you might see with let here is this is a more subtle error. I've accidentally typed a C after the :as. Not a problem. It compiles, it runs, it returns just fine. Until I actually try to use C, and then it's not there. So this is an example of, even though we have the macro doing the parsing for us, it's just missed a part for this pattern. So it's not quite a complete checker. Well, let's look at the code for this grammar here. Maybe we can fix it. Or maybe not. Well, this is a handwritten parser, so it's actually a really nice, it does the job, and it actually has a lot of error messages in there, and it tries to get through all of the contents of what you expect to find. Unfortunately, it is handwritten, it is complicated, and just adding that one part in here to make sure that you can't have symbols following the :as might be a bit tricky. There might be not side effects, but you might have consequences that ripple throughout this block of code. Okay, so let's talk about the project that I'm working on that was spawned by the Fortifying Macros paper, and just try to give it, first of all, I have no idea how to name things, so if you have any ideas, I'm open to suggestions after the talk. The goal of this project is to help define illuminated macros, which essentially boils down to good syntax documentation and good syntax error messages. There are other things that we talked about which we're going to try to get to in the future, but for now, that's what it's solving right now. Okay, right in the middle of right at the base of this project is a new function called parse forms. The way parse forms works is it takes 2 arguments, a as yet undefined syntax that I will describe, but just not right now, and some kind of input, some kind of set of input. So in this case, it's something that looks a lot like let. And the return value of parse forms is whatever that let syntax returns. I'll get into that in a little bit. But if it doesn't, if it can't parse it, it's just going to try to print out some kind of error message. Remember that :a that we saw? Let's look at another example of that, this time with what parse forms returns for an error message. Just as a caveat, I'm not entirely thrilled with this output, but it at least captures the 3 things I want to capture. So more work is needed to make it prettier, but it essentially captures the essence of it. First of all, this is showing us exactly where there was a problem in the form. It's showing us exactly what happened. There was a bad value. And it's showing us why it was a bad value, by showing us positively what we were expecting to see. So that's the 3 things of a good error message. You can actually probably, if you were a new person looking at this code, you have a shot at fixing it without resorting to a web page. Okay, so that's parse forms. I wanted to try to step it back a little bit, or make it a little bit more convenient to use parse forms. It's after all just a function, so of course we have to wrap it in a convenient macro. In this case, the macro's name is defsyntax. It defines essentially a macro. What's different between defmacro and defsyntax, while they both take, for example, in this case, let as the name, defsyntax only takes 1 argument following it, and that's the syntax of the macro. Again, I will get into that syntax in a little bit. So, it's essentially expanding to def macro let ampersand forms, and then it just calls parse forms. That's the essence of it. Now, there's a reason you want to use def syntax rather than just saying def macro or, and calling it yourself. And the reason is because it exposes the syntax, that so-called let syntax up there, it exposes it for other tools to describe it. So there's another tool called syndoc, which prints the syntax for any macro that has been defined using def syntax. So let's look at that. Again, def syntax, let syntax, and here I'm printing out the actual grammar of that syntax. This is generated code, and it's color-coded because it's generated, I can color-code it. And this is the complete grammar of let. It shows binding vecs, it shows how to destructure maps, and it goes through all of the detail. This is considerably more complete, in fact it is complete, for what let does, and the syntax that let requires. I think, just as an aside, this is the only source of documentation right now that has this complete picture of what let does. So this slide will be available after the talk. Okay. All right, but that's showing the output. What you guys want to see is the input, or rather, how do we actually go about making these magic grammars that show up in such pretty colors? So, what is it? Well, at its core is a library called sequence expressions, or seekx. This is essentially regex, except that it's essentially regex for all of Clojure values, not just characters. So if you want to think of regex as something that does pattern matching and pattern capturing on a single string of characters, this can do the same effective thing, but this time across a string of Clojure forms, or rather Clojure values of any kind, be it integers, sets, data structures of any kind. Which is nice. I'm going to start by showing an example. I'm going to build it up over time, and this is the actual grammar for the let form that we saw earlier. So down below, again, we have def syntax let. So this is a macro. And it has some various features that describe the grammar. So cat, that just stands for concatenate. And it means that we're going to concatenate all the subforms underneath it. Vec form is the first form, and rep star is the second form. Rep star is merely the repetition pattern. It means 0 or more. Vec form is a literal. It means this is a literal subsection here, and it's going to be a vector. Well, what's inside the vector? Another pattern. In this case, rep star. So there's going to be 0 or more binding pairs. Just for clarity, the form is a default, and it matches any one thing. Binding pair is not defined. We have to define that. So let's define that. Here we have a def, it's just a var, and it's bound to a rule called binding pair. There's nothing special about the rule, it's just labeling it so that when we print it out on the screen, it looks good. And it's defined simply as the concatenation of a binding form with a form. For convenience, I've made another macro called def rule that simply combines def binding pair with rule binding pair. In this case, it's def rule binding form. And it is defined as the alternation between either a symbol or binding vec or binding map. So the last one I'm going to look at is binding vec. And it looks like this. As you can see, it's a vec form, so it's some kind of literal vector. Inside it is the concatenation of 0 or more binding forms, followed by an optional symbol ampersand, followed by a symbol, followed by an optional keyword as, followed by a symbol. Okay, so what's tricky about this particular one is binding form is actually defined after this one. So it's a recursive grammar. In order to get at grammar elements that have been defined after you, I had to declare it up front, up at the top, as you can see it. And then because it hasn't been defined yet, I had to wrap it and protect it with a delay. This is an example of using existing Clojure constructs to just protect us, and now we are able to describe grammars that are recursive in nature. Okay, so that shows the definition, almost the complete definition of what is in the pattern of a grammar. But there's two aspects of sequence expressions, just like regular expressions. There's pattern matching and pattern capturing, or input capturing. So I'm going to show you some of the input capturing features. In essence, there's only two parts to it. There's a cap function and a recap function. Cap is for capturing actual raw data that comes in. In both of these examples, you can see that cap binding form and cap form are capturing 0 or more forms underneath them. So what's recap? That is something that allows you to get access to all the things that you have already captured thus far in the pattern. So as you can see, underneath recap is that whole sub-pattern. The input to recap, or rather, what recap gives you is a function that can access the captured elements thus far. And the output of that captured function becomes a model that is available for further use later on in the pattern. So in this particular example, I'm capturing the binding form, destructuring it because there's only one item in the binding form. Same thing for the value, I'm destructuring that and getting the first item out of that. And then I'm just returning it as an object. This is probably going to be one of the harder elements of this to explain, but I don't have a lot of time to talk about this, but this is, I think the important point here is that you can, it's arbitrarily powerful. You can describe caps anywhere you like in your code, in your pattern. You can define recaps anywhere you like above those and apply any Clojure function to those. And the output of that Clojure function becomes available for future recaps up the stack. Okay, so that's the idea, or that's the example of using it. Let's talk about the ideas in sequence expressions and why some of these ideas are nice. The first one, of course, you're all familiar with is sequence is the importance of data. At the end of the day, the syntax is data, and that allows the syndoc function to traverse that grammar tree and generate rules and print those out in a pretty way. Likewise, automatic error messages come out of this. Because the grammar is available, we can parse it, and the results of that parse become an abstract syntax tree that we can track, and we can find out where things went wrong and find out, by looking at the original grammar, where things could have gone right. And it's not the end of it. Because we're starting with data, we don't have to end with a specific closed set of tools. We're open to future improvements as we go forward. So another aspect, I think Chouser mentioned this, was the idea of trapping DSLs or the idea of escaping from a DSL. Well, I made a conscious decision here. I think you saw the vec forms and kind of the cumbersome use of vec form, or why didn't I just use vector in that position? Well, because I didn't want to have any escaping. I wanted you to be free to use this as just a library, not a DSL that you can go into and then you have to run away from when you want to do real work. So the idea is, it's just functions. There's actually no macros in the sequence library itself, the sequence expression library. And it's defined underneath as a protocol, as all good programming Clojure libraries do. So you can extend it to everything. Just as a practical example, all of Clojure's literal forms, vectors, numbers, strings, sets, etc., have been extended across this protocol. In fact, they match exactly one occurrence of themselves. And that's the definition of a literal. So if you want to stick a number in a sequence expression, it is. It's there, and you can just use 1, and that is a valid expression, and it represents one occurrence of the number 1. And that's on purpose. There's no escaping needed. There's no special form that gets you out of this DSL. If you haven't typed a special form, or a special function name, then you're not in the DSL. So you can define it however you like. Or you can use it or not use it as you see fit. This last point I want to make is probably the most, like I was alluding to earlier, the hardest point to talk about. There's two elements to sequence expressions, the matching portion and the building portion. And it mixes both of them very consciously together. So this is a very controversial complexion of two types of functionality. You have your patterns. They're arbitrarily powerful and complex. You have functions built into that. Those are functions, therefore arbitrarily powerful and complex. So that's bad, right? It makes it, well, there are downsides. I'm going to start with the first one, which is simply makes the pattern harder to read in the source code. That's because the source code has been polluted, if you will, with captures and recaptures and more recaptures. So that's your trade-off for using this code to using this library. You end up with patterns that are kind of hard to read in the source code. So unlike macro by example, you can see that we've not even tried that to go for that goal. Now, that is mitigated somewhat because we can use syntax-doc or syndoc to print the syntax out on another channel. So you are actually, while you can't read it in the source code, you can certainly read it elsewhere, and you can display it in other ways. Another advantage, though, of having this mixing of pattern matching with pattern capturing is they're composable blocks of code. So one syntax expression defines both things, and you can reuse that chunk in other syntax expressions. I'm going to show a quick example of that. So here's defin, as defined using the syntax expression library. It has, the bottom part is a set of optional doc strings, attribute maps, and an alternation between a single signature body or a literal list form, one or more literal list forms that have signature bodies in them. It's not, the terminals are just a shorthand way of telling the grammar to say, that's great, don't print any more underneath this. This is an endpoint as far as that. We get the idea. When we see the attribute map, we know it's a map. Okay. Signature body is borrowing the binding vec from let as its first part. So whatever that work is being done there, both in terms of matching and in terms of capturing, is being lifted and put into here. So it's a very easy and composable way to take your code and define arbitrarily complex grammars, and then define and reuse those bits and pieces as needed throughout your stack of macros. And just for completeness, this is the full syntax for defin. Again, I don't think this is available anywhere else, so this slide will also be available after the talk. Okay. So that's the end of the talk, and we have described illuminated macros as having basically 4 things that we like to see. Is we would like to see good documentation, we'd love to see some good error messages, and we would like to see additional advanced tools that help both the developer of the macro and the user of the macro to see how the input is being compared to the actual syntax and how the input is being compared to the actual output. And that's the URL, by the way. That's it.
We should have time for a question or two. Anyone have any questions?
Yes.
Stupid question. Do you show how to generate output code once you parse?
The output code is
It's the model.
This is the code.
No,
that's the code.
No, he's talking about the output. The model. So after you've captured it, it's this one here.
Oh, I'm sorry.
Right. So that's the capture. So if you were to use this exclusively for a macro, it would be in those capturing functions. Like that little anonymous function there is where you would be building up the output form, and then it would come out just like that. Because it's, as he said, it's an arbitrary complex output capture as well. And so that's what your output form, where your output form would be built up. Does that answer your question?
Yeah, I didn't see doing that in defsyntax.
Oh, okay, good question. So the question is, where's the output for that syntax? I have not put in this example the capturing code. The reason is, I couldn't fit all of that on one slide. So the idea would be, there's 2 ways you can think of using this, or if this helps to think about it. One is simply to capture everything, and then just to send that to Clojure's built-in let. That would be basically treating all of that grammar as simply a validator. But the more advanced usage would be to capture at various key points all of the information, for example, at binding, returning maps, and then finally generating your output from that result. At the bottom level, there would be a final lowest level recap that would produce something that would say let star, et cetera, et cetera, et cetera.
Okay, one last question.
So I'm curious if you guys have a way to do something like tracing the expansion. So in several scheme systems, you can actually say like trace define syntax, and it will show you the input form, and then it will show you the output form for that as the expansion is occurring.
We do not. The question is, do we have a way to trace from the input to the output? We want that. but we
Right.
do not have that.
The closest we have is the same macro expand that we have for other Clojure macros, which only shows you the final output, right?
Because we have the grammar as a tree, and because we have the results of parsing it as a tree, there's no reason we can't do that. Except time.
I had two other pieces. One, just for the record, syntax case does allow you to do arbitrary computation.
Oh, okay.
And two, another thing that might be interesting to look at, it's interactive, but you may have already run across it before, but it's Ryan Culpepper's macro stepper, which is part of the Racket system as well, which gives you an interactive tool to actually step through the expansion of the macro and see kind of where it went wrong.
Okay.
Yeah.
So that's another thing you guys might.
The scheme folks have done a lot more work on more complex macro languages than we have in Clojure, yeah. So, well, that's all our time, so thank you.